Now, okay, so hello, I'm Alejandro Piñeiro, I work for Igalia, and in this presentation I'm going to talk about how we use gfxreconstruct and apitrace for performance evaluation. So when 4 years ago we started the Vulkan driver for the Raspberry Pi 4, our first objective was getting Vulkan 1.0 conformant, and after that we did a lot of work for performance. We made that more later, usually after each conformant at 1.1 conformant and getting 1.2 conformant, but was there when we did a lot of work on performance. So at that time, what we focused the performance work on Unreal Engine 4 samples. They were pushing a lot what the Raspberry Pi 4 was able to get. They were really generally GPU limited, and they were using really expensive shading. So that means that most of the focus of this implementation work, performance work, was done on the compiler. That has also the advantage that it also benefited the OpenGL driver. So this is rendered by the Raspberry Pi 4. This is one of the Unreal Engine samples. So what the process at that time was, we get the sample running, we capture the shader code, we identified non-optimal code stresses, we figured out what we could do to improve that, implemented an optimization, and then we need to verify the outcome. We use v3dv, we use manual testing, and we also use gfxreconstruct and apitrace. So those are tools that they allow you to capture the calls to the API, so Vulkan calls in the case of the gfxreconstruct, or OpenGL calls in the case of apitrace. So here we have a port of DOM 3 on one side and Unreal Engines in the other side. What was the two main uses for these tools? One was visual checking for artifacts, because sometimes when we were doing some improvement, we suddenly get some artifacts, but were not, in some cases, were not like, okay, everything is wrong, but like we were, going in a corridor, and for example, some flowers or some lighting effects, instead of seeing it that correctly, have some blinking that were not correct. So we needed to visually checking for that. And having the traces allow us to just put in the trace to run, and just we was looking for it. And we also use that for performance comparison between before and after the improvement using the FPS. We created a script for that, so we have all the traces in one directory, the script took all the traces from that directory, and with time, we started to add some parameters. Because, for example, on average, we run these traces several times, and we got an average of the frames per second. Advantages. That made visual checking far easier, because the alternative was like putting the sample and started to fake playing the game, going for corridors, and that was boring. Also, in the CI, just in case someone is wondering, on the CI, there are some cases of having some frames and checking the outcome, but that was, as I said, that was not enough, because sometimes you need to, go into the corridor, and the artifacts were not always in the same place. Also, the frames per second was really easy to understand, and at the beginning of performance work, it was evident for some specific improvements to see that it was a really improvement. The problems. The frames per second is unreliable. For example, if you run the same trace with the same things, sometimes you get a different value, because there's a lot of things that can affect the frames per second. And now that we did this performance work, getting just with the frames per second, if we get an improvement is minimal. So at this moment, we use this frames per second measure, we use that mostly at a sanity check. We implement an improvement, and at least the frames per second shouldn't go down. Well, this is the content. Sorry for talking so fast, but this is an allotted talk. So this is the end.